Okay. So this is what we have learned only. Just you go through it. So first we have already learned angular position. Angular position we represent with R, and here it is given in terms of phi. So that I don't think you have learned. So you can just write only that terms. No need of writing everything because this is all we have already learned. So first position, just to give special term, the terms related to rotational motion. You give terms related to rotational motion. So this is the same thing we have learned it. So you don't have to go for again. First angular position. Angular position. Angular position phi is equal to length of the arc subtended. That is, angular position phi is equal to, just learn that equation is enough. Length subtended by the radius. Length of the arc subtended by the radius. That is angular position. Angular position phi is equal to length of the arc subtended by an angle phi. So L by R. And direction of rotation, just mention direction of rotation. You can just mention anti-clockwise direction. Anti-clockwise direction. That's enough. But angular displacement theta. Angular displacement theta. You can write it. Change in position. Change in position. We have already learned same thing. Change in position. And SI unit is radian. SI unit is radian. In other ways, bracket you can write. Bracket you can write radian value of angular position phi. It is the radian value of angular position phi. That is how this and this is connected. Okay. It is the radian value of the angular position phi. Next, angular velocity omega. This is what I have asked you in your periodic test. Do you remember? And majority have written the SI unit radian. Instead of writing radian per second, you have written radian. That is why majority of you lost the marks. I know that your performance was not good. I did not forget to ask about it. But I know, why should you give? Next time you will do. So I believe that you must have spent more time in writing investigative project and all. That is why you got very less mark this time. I remember even the student, those who really study, and some of them are got very less marks as we compare to our first periodic test. Clear? So please see that you come up. So next is angular velocity omega, theta by t. With that you can write del omega also is equal to d theta by d. This is the magnitude. If there is a change, then you can write d theta by dt. We already have learned. And unit of angular velocity radian per second. Linear motion meter per second. Here it is radian per second. This and all just this is we have already discussed. So I don't have to draw. Just write because it is a revision. I hope you have completed that. Then afterwards you have learned angular acceleration. Alpha. Do you remember that? Alpha is equal to change in angular velocity by time. So alpha is equal to change in angular velocity by time, or we can say omega minus omega 0 by t. In linear motion it is v minus v0, but here it is omega minus omega 0. And unit radian per second square. In linear motion meter per second square, here it is radian per second square. That means The velocity changes from position time is equal to 0 to the time is equal to t. That's it. So already you have learned alpha.
Can you show angular velocity once again?
Okay. I'll write here. The angular velocity, change in angular velocity is equal to d theta by dt. Or we can substitute this also. Instead of d theta, you can write final velocity divided by that way also you can write. Okay. D theta by dt unit is radian per second. If there is no change, it is the final equation. Omega is d theta by, there is no change, then if omega is constant, angular velocity constant, you can write theta by t. If it is changing, d theta by dt. Okay? Okay? Sanya?
Yes,
Like,
ma'am.
this is also over now?
Yes, ma'am.
Okay. Now, this is the equation again, please write. Equations of motion, linear motion. Here we have angular equations of rotational motion. You can write the heading angular equations of angular equation.
Ma'am,
Yes.
ma'am, can you show angular acceleration again?
Okay, okay. Yeah. Wait, others plus wait.
Yes, ma'am.
Okay.
Finish.
And the rule here already I have explained to you right hand school or right hand cork school. Here also we are come to because rotation we are taking it anti-clockwise, correct? So actually the motion is in terms of a curled fingers and the quantity acceleration is represent thumb. In torque it was torque representing thumb and the other two quantities are representing the fingers. In this case, acceleration representing the thumb and other two quantities, that is change in velocity, change in time representing the curved fingers. That is only difference. So all these are one rule, right hand thumb rule or right hand screw rule. And we always take it in a anti-clockwise direction. That's just for your knowledge, just mention because we don't have to go much detail. Can I change? Okay. Next, angular equations of rotational motion because we are discussing rotational motion, no? Angular equations of, we have learned equations of motion. Now, angular equations of rotational motion because energy, conservation of energy everywhere. So, you can just copy down all these equations. First one, omega is equal to omega 0 plus alpha t. We have here it is v is equal to u plus at. You remember? So analog to this one, we have this. Omega initial omega final velocity, omega 0 is the initial velocity. Okay. This is first equation. I'll tell you. Don't write the second one. I'll tell you when to write. This is the second equation of motion. Okay. And this is third equation of motion. That is omega square is equal to omega 0 square. Omega square is equal to omega 0 squared plus 2 alpha theta. That's the third equations of motion. This is corresponding S is equal to ut plus half at square. Corresponding equation. This is you know v squared is equal to u squared plus 2as. And this is all are about the derivation. Don't no need of studying that. Okay. And there are certain things we require that I'll explain to you. Some equations apart from this, one, two, three. There are two, three equations we require to know that I'll tell you after writing these three equations of rotational motion. After writing three equations of motion, we can write it as for average angular velocity. So that is the one, this one. That is omega plus omega 0 by 2. That is equal to theta by t. In analog to the linear motion, we have v plus u by 2. This is for which one? This is for constant motion. Constant motion, suppose the rotational motion has moving with the same velocity without changing, then we can find out final velocity plus initial velocity by 2. That is actually equal to theta by t. That is a linear motion, displacement by time. So this is that equation. So using that equation only, we are getting all these equations. That's why this is and all. Okay. This is and all. From this, we are going to get this second equation. You don't have to copy that. Only this four equation is enough. Okay. First, omega 0 plus alpha t. Second one, omega 0 t plus half alpha t square. Then omega square is equal to omega 0 square plus 2 alpha theta in analog with the three equations of motion. Okay. Can I change? Okay. So this is a summary of that. Summary of that. Four equations and as well as summary of that. Okay. Omega 0, all that. You can just take a screenshot if you want. You can take already have written. If you want, you can just take a screenshot of this slide is enough. You don't have to copy. Just take a screenshot. Same thing we are doing it. That's all. There's no difference in that. This is t. Omega 0 into t by 2. Just take screenshot. That's enough. Are you writing? I thought of saving the time. And over. Problems we will do later. Yes. You can take this screenshot of entire study summary, what you have learned so far. Okay. This is straight line motion versus rotational motion. Okay. We have already explained everything, but this is a small summary. If you learn this table, you will come to know. And this is what is left with us. This is what we are to learn now. The first inertia. That's the last. It is left with it. Inertia. Second law we have proved in the case of angular momentum. Now you are left with the first law. V omega T times same acceleration. Here it is A, rotational motion, it is alpha. Inertia. In inertia, you know, it is the ability of a body to resist. Similarly, that is what left with we are going to learn. Inertia, and in the case of rotational motion, it is I. Then, effect of the force. Here it is capital F, here it is tau. So this is an analog of translational. That means linear straight line motion plus rotation motion. Okay. Now we are moving on to last topic, inertia. What is inertia in case of rotational motion? Can I change? This and all over. I'm not going to that. And do you remember, this is also repetition. Relation between linear velocity and angular velocity also we have learned in the previous session. V is equal to R omega. Do you remember that? So this also you can just write it down. Relationship between physical quantities measured in angular motion and that in linear motion. Relationship between physical quantities measured in angular motion and that in linear motion. So left hand side is linear motion, right hand side of the equation is the angular motion or rotational motion. First, linear displacement, angular displacement. S is equal to R theta. You can write everything according to that. If you are taking screenshot, well and good, I can just skip off. You take lot of time. If you take screenshot, you will get a picture also if you want. Then afterwards, you write. This is, then this also we have learned V is equal to R omega. So how we are getting also is written here. S by T linear velocity, R theta by T angular velocity. So same thing, repetition. One more thing you have to write. Acceleration, linear acceleration. So after continuing that, this repetition, you can write under this third one. You write linear acceleration versus angular acceleration. Angular acceleration. Relation between linear acceleration is equal to angular acceleration. That is A is equal to, the relation is A is equal to R alpha. Third relationship what we have learned, acceleration is equal to R alpha. And I have asked you many questions from this also in the last periodic test. All made mistake out of it. Okay, so that is our next period and frequency object. Next heading, just write the equation, that's enough. The period and the frequency of an object in rotational motion. This is also what we have studied. Frequency is the, so just write this one. Because we require in next year also. Time period we have already learned in the last lesson, no? In that. Laws of motion we have already learned in that. So you don't have to write that definition. Time period means the time taken by one complete rotation. Frequency means number of rotation by object in 1 second. So what you have to write once again is the frequency. That is, in linear motion, frequency is equal to 1 by t, but in angular motion, it is omega theta by t. And instead of theta, we also can write omega 2 pi by t. And then instead of t, you can also substitute 1 by f. Then you will get finally omega is equal to 2 pi f. Why? Because frequency is equal to reciprocal of time period, or time period is equal to reciprocal of frequency with that relation.
Ma'am,
Yes,
is it 2 pi?
2 pi by t, time period. Then instead of t, we substitute 1 by f. Then cross multiply, you get 2 pi f. It is, you have written in laws of motion chapter. Can I change, children? I hope you completed. Yeah. So now you come to the last session of this chapter, moment of inertia. Okay. In linear motion, we call it inertia is the ability or tendency of an object to resist its motion. Similarly, moment of inertia, moment of force, moment of angular momentum. You see, in rotational motion, we use the word moment. Okay. So what is moment of inertia? It is the tendency on object, okay, to resist the rotation about the axis. Okay, same as it is. Only thing is, it is rotation about the axis, but we have learned linear inertia, that is a straight line motion, but this is about the rotation. So, moment of inertia means it is the property of a body. Property of a body. This are not don't write. I will tell you what I am saying. You write. It is a property of a body, rigid body. Property of a rigid body to oppose change in to oppose change in to oppose change in rotatory motion, changing rotatory motion, change in rotatory motion, rotatory motion about an axis. Rotatory motion about an axis. You can roughly just draw this figure. So what is moment of inertia? Moment of inertia is the property of a rigid body to oppose the change in rotatory motion about its own axis. The even fan is rotating about axis, it has a tendency to come back to the original position, but electrical energy overcome that resistive force. That's what. And how can we measure the moment of inertia? Moment of inertia we represent with the capital I. Moment of inertia represent with the capital I. How can you calculate? It can be measured. It can be measured. It can be measured by the product of It can be measured by the product of mass of a particle, product of mass of a particle and square of the perpendicular distance. Same only. Only thing is here we are taking the square. Square of the perpendicular distance. Square of the perpendicular distance between the particle and axis of rotation. Between the particle and axis of rotation, or otherwise from the axis of rotation. Perpendicular distance from the axis of rotation or between particle and axis of rotation. So I hope you must have drawn this figure roughly. Now you can write the equation. Therefore, I is equal to mr square. Moment of inertia is a scalar quantity and SI unit mr square, that is kg meter square. SI unit is kg meter square. Okay. So now we are going, this is for a one particle. So you know that total moment of inertia of the system will be the sum of the individual moment of inertia of each particle. Okay. So we consider in that way what we are going to get total moment of inertia of a system. So next heading, total moment of inertia of a system. So you can just draw a system like this. There is axis.
Ma'am,
Yes,
can I tell the topic once more?
slide up.
No, heading.
Inertia of a system. Total moment of inertia of a system. So here you can write M1. Here it is M2, another particle. Somewhere here M3, another particle. Somewhere here M4. And somewhere here you have M5. So just think this is the axis of rotation AB. Then the distance we can roughly represent up to M1. It is R1. It is M2 particle. We have R2. It is M3 particle. It is R3. And it is M4 particle. M4 particle. We have R4. And M5 particle. It is R5. This is axis. So you can write it down, children, below that. Consider a rigid body. Consider rigid body. Rotate about an axis AB. Consider a rigid body. Rotate about an axis AB. With masses of particles. With masses of particles M1, M2, etc., M5, and corresponding distances and corresponding distances from the axis.
Ma'am,
Yes,
can you say again?
consider a rigid body, rotate, consider rigid body, rotate about an axis AB of particles, masses M1, M2, etc., My, M5, and corresponding distance from the axis R1, R2, R3, R5. Then total moment of inertia. Total moment of inertia of the system is equal to sum of the moment of inertia of individual particles. Sum of the moment of inertia of individual particles. Thus, moment of inertia I is equal to M1 R1 squared plus M2 R2 squared plus M3 R3 square plus M4 R4 square plus M5 R5 square. That means sigma Mi Ri square. We can make it the summation sigma Mi Ri square. Sigma Mi Ri square. Next line, as we have center of mass of the system, as we have center of mass of the system RCM, then total radii of the individual particles of the system, individual particles of the system in a rotational motion, in a rotatory motion, instead of rotation, you can also write in a rotatory motion is measured as radius of gyration. Radius of gyration. Radius of gyration bracket K. Radius of gyration K. So since in rotation motion, if all the particles have total moment of inertia, everything is concentrated at the particular center. Similarly, individual radii also we can assume to be concentrated. Therefore, moment of inertia is equal to, instead of R, we can write it common radius of gyration, total radius of gyration. I is equal to mk square. So mk square and as well as sigma mi ri square both are same, because instead of this ri we have
Ma'am, can you tell again what is radius of duration?
as we have center of mass of the system RCM, then total radii of the individual particles of the system in a rotatory motion, also measured as radius of gyration. So just like moment of inertia, we take it as total sum of the radius. Similarly, in the case of radii, also total radius of the system, also we take it as the sum of the individual radii. So that total radii of individual particle we represent as one individual term, that is radius of gyration. Radius of gyration. So if you substitute radius of gyration, we know in a circular motion, r is the radius. So wherever is the particles, r going to be radius. So instead of r, we can represent k also. So in that case, moment of inertia, we can represent I is equal to mk square. So that is why I tried to say. Clear? Okay?
Yes, ma'am.
Okay. So even from this, you can also find out k square. That is radius of gyration square is equal to I is equal to capital M. Therefore, k is equal to square root of moment of inertia divided by total mass. If you want to find out the radius of gyration of the system, we can take the square root of I by M. Then you will get that. Okay? Yeah. Okay, children. So I wind up the session. We will meet next class. Okay. Thank you.